event of the afternoon is Porter Williams talking about Julian Schwinger and the Audacity of scope.
Thanks for having me. So I'm going to round out the history afternoon with what's probably the most straight bit of history that we'll get, in the sense that there's no sort of grand philosophical payoff at the end, although I think there are things that are philosophically interesting along the way that I'll kind of try and flag. The other thing to say is that this is part of a joint thing I'm doing with Mike. We kind of came at the same project from different directions. Mike, a couple of years ago, did some work on the origin of Euclidean Green's functions with Schwinger in the sort of early to mid 50s. I was kind of working backward, looking at the history of effective field theory, and we kind of converged on Schwinger in the 50s and 60s. So Mike's name is not on the slide, which he will probably be grateful for in about 45 minutes. But this is joint work. All right. So as many of you will know, Schwinger I think it's fair to say Schwinger was probably the central architect of quantum electrodynamics immediately after World War II. So he's most commonly mentioned along with Feynman and Tominaga, and doesn't have the cult of personality that Feynman does. But what's important is he went far beyond just developing renormalization methods for quantum electrodynamics. I think it's fair to say that Schwinger was integral in laying the foundation for post-war QED and for quantum field theory itself. So this is just kind of a scattered greatest hits of Schwinger between 1948 and the early 60s. What everybody knows about are the first two things. He then writes, he gets into this habit of writing like, 4 or 5, series of papers that are 4 or 5 papers long, where he lays the foundations for QED and then sort of decides he doesn't like exactly what he's done, and redoes it. In fact, this is in the first talk yesterday, and Wayne mentioned this Tominaga-Schwinger picture of defining states on hypersurfaces, and then time evolution operators moving you locally between bits of one hypersurface toward bits of another. That's the work I'm referring to in this dynamical foundation for QED line. He introduces Green's functions methods, which now everybody who's ever calculated a scattering amplitude has seen quite a bit. There's a paper in 1957 where he introduces the notion of dynamical symmetry breaking. I'll say a little bit about this later. And then in 1962, he introduces what gets called the Schwinger Model, which is, as far as I know, the earliest explicit model that contains confinement and dynamical mass generation. The Schwinger Model is QED in 1+1 dimension. It's very cool. And so he's awarded the Nobel Prize in 65 for the QED work, along with Feynman and Tominaga. Dyson is excluded because only 3 people can get it, which is a dumb rule. All right. So we're going to not say a ton about, let me put you in the frame of mind of a particle physicist in the 50s and 60s. QED has been very successful. The natural thing to do is to start trying to use quantum field theory to model weak interactions and strong interactions. But as many of you will know, extending the methods that were so successful in quantum electrodynamics, namely the perturbative renormalization methods. This goes poorly for the weak interactions. The model of the weak interaction was the Fermi-on interaction model. That's non-renormalizable. So you couldn't use the renormalization methods that were so successful in quantum electrodynamics. You couldn't use perturbation theory to calculate strong interaction phenomena. That was a real problem since basically the calculational tool that people had at the time was perturbation theory. So quantum field theory very quickly kind of ran into a wall after the success of QED. And this was a particularly pressing sort of theoretical, you might say phenomenological problem. There was, at the same time that quantum field theory is proving itself inadequate to the task of modeling weak and strong interaction phenomena, there's a massive, so post-World War II, the accelerator community sort of really starts to get moving. And there's this influx of, in particular, strong interaction resonances, very short-lived particle states. This is just a chart from one of Schwinger's early papers where he's laying out the various strong interaction resonances he's trying to model. But the point is just that at the same time quantum field theory is proving itself inadequate, there's this big influx of accelerated data that particle physicists are desperately trying to model successfully. And so by the 1960s, many particle theorists have abandoned quantum field theory. They thought that the success of quantum electrodynamics was kind of a one-off, and that a different framework was necessary for modeling weak and strong interaction phenomena. Yeah, as many of you will know, they started working on S-matrix theory. They used current algebra methods. They turned to dispersion relations, and so on. There's this proliferation of theoretical frameworks in the late 50s and through the mid-60s, just because it's a fun way to use this paper. This is Wilson writing in '65 about the state of particle physics. The Hamiltonian formulation of quantum mechanics has been essentially abandoned in investigations of the interaction of pi mesons, nucleons, and strange particles, so strong interaction phenomena. This is a pity. And then he goes on to sort of sing the praises of the Hamiltonian approach. But so this is in '65, and he's sort of giving a brief summary of the state of the theoretical state of play. Schwinger, on the other hand, did not abandon quantum field theory as so many of his colleagues did. He thought that quantum field theory had been unfairly equated with perturbation theory, that there was much more to explore in the theoretical framework, and stuck with it through the mid-1960s. This is not quite right, the quote here, but it sort of captures both the flight from quantum field theory in the particle theory community and Schwinger's sense that he was working, he was not part of a large community of people who were working on field theory. So he says, I think I was the only person through the 50s and 60s who kept up the belief in field theory. As I said, that's not true. In fact, there's another one, Wilson, that turns out to be important. Okay, however, after 1965 or 1966, depending on whether you take the date of conference presentations or actual publications, Schwinger ends up abandoning quantum field theory. He moves on to try and build a more phenomenological framework for doing particle physics, which he calls source theory. I won't say a ton about source theory in this talk, but I'm happy to say more in the Q&A. So the big picture of the project that Mike and I got interested in is that when you look at source theory, a lot of the sort of the physical concepts, the calculational strategies that he's using, and a lot of the methodological commitments, in particular, a sense that one ought to refrain from making speculative extensions of your theoretical framework to arbitrarily short distances if you don't have to. These are all the kinds of things that drive Schwinger to source theory. And if you look at sort of the history of the effective field theory program as it emerges sort of in the late 60s through the early to mid 70s, there's a lot of superficial overlap between the considerations that effective field theorists are bringing to bear on their project and the things that drove Schwinger to abandon field theory and develop source theory. So the big picture question that at least got us interested in this is, like, why didn't Schwinger figure this out? Schwinger could calculate everything, like everything you could possibly ever want calculated. He understood quantum field theory at least as well, if not better, than almost all of the community at the time. What prevented Schwinger from developing the effective field theory framework himself? I will speculate about that in the Q&A if you would like. Today, what I'm going to do is zoom in on some aspects of his work between 1954 and 1965. And the idea here is just to focus on his understanding of certain aspects of field theory that eventually drove him away from it. These are interesting not just for the role they play in his turn to source theory, but also because it reveals that Schwinger had a fairly, like a pretty philosophically sophisticated and somewhat idiosyncratic view of a lot of issues in field theory at the time. All right, so first I'm going to talk about how he understood the physical import of renormalization and the role that it served in quantum field theory. I'm going to sketch this novel argument he gives and then later abandons for the inconsistency of quantum field theory. This is another thing I'm happy to say more about in the Q&A. In particular, there's a whole bunch of gross Green's functions machinery that I left off slides, but I'm happy to talk through if you have questions about it. And then the sort of end of his quantum field theory work in the mid-60s, he ends right as he's developing this principal distinction between the notion of a fundamental quantum field and the notion of a phenomenological quantum field, and he's trying to develop a mathematical schema for relating these two things. So that's where we're going to end up, and that's basically where his contributions to quantum field theory leave off in the mid-60s, and source theory picks up. Okay. So I'll start by talking about renormalization. As many of you have heard, there's a kind of, in fact, I think you've heard today, there's a kind of just so story about renormalization that goes as follows. Before the development of renormalization group methods, renormalization was recognized in the physics community as sort of uninterpretable, physically uninterpretable hocus pocus, a dippy process for removing divergences. These are Feynman quotes from the popular book he writes about QED in '85 or something. And indeed, Feynman himself has certainly contributed to this picture of how the community understood renormalization methods in the 50s and 60s. The second part of this just so story says that it was the work of Ken Wilson, Michael Fisher, Leo Kadanoff, Franz Wegner, et cetera. This list can kind of go on for quite a while. That first made it possible to do two things. One, understand or attribute physical meaning to the renormalization procedure. That you had some physical picture of what was actually happening when you're doing renormalization. And second, it was only after the development of RG methods that people could recognize that renormalization, it doesn't have any essential relationship to the removal of divergences in perturbation theory. I've called this a just so story. Like, I am not innocent of having done this. I'm sure that if you go look at my dissertation, you'll find this and, well, this and much worse, but certainly this. Just to substantiate the claim that this is in fact a story that gets propagated, certainly in the physics community. This is a quote from a nice quantum field theory textbook. In spite of its successes, the renormalization procedure could still be seen as some kind of prescription or recipe to get rid of the divergences in an ordered way. This is talking about prior to Wilson. This discomfort about renormalization was expressed on occasion by comparing it with sweeping the infinities under the rug. After the work of Ken Wilson, the process of renormalization is now understood in a very profound way as a procedure to incorporate the effects of physics at high energies by modifying the value of the parameters that appear in the Lagrangian. So this is the story we know. The post-Wilson picture of renormalization is that you remove some high energy physics from your Lagrangian and you bundle the contributions of that physics to scattering amplitudes into a renormalization of the parameters in the remaining low energy effective field theory. Similarly, this is a picture that John Carty, who's a physicist at Oxford, drew of himself and put on his website. It's like sufficiently haunting that I wanted to put it on the slide. So this is Carty writing a retrospective about Wilson. He says, before Wilson, the role of renormalization in field theory was itself poorly understood. The manipulation of infinities was still viewed with suspicion. After Wilson, that all field theories are merely effective descriptions of nature at particular energy or length scales began to take root. And he talks about how we came to understand renormalization as just requiring renormalizability amounting to require that we have a theory that be largely decoupled from whatever high energy physics would UV extend it. Okay, this just so story, as with most just so stories, is not quite accurate. And what I'm going to talk about today is how Schwinger does not fit nicely into this just so story. But it turns out that if you actually go look at this literature in the 1950s, You'll find also a large group of people working in Japan who have a fairly different story about the physical significance of renormalization in the 50s. More generally, it's somehow not surprising that if you give a bunch of physicists a successful, a mathematically suspect but physically successful method, they might try and put some physical meat on those bones. So that's more or less what you find in pockets of the literature in the 50s. Schwinger's contribution is what we're going to talk about for part of the talk today. But just in case you wanted like a fairly clear statement of Schwinger bucking this trend, these are from lectures that he gave at Stanford in the summer of 1956. It says, renormalization is concerned with long and short space-time intervals as they affect the measured physical mass of a particle. Renormalization is required even in a theory that contains no divergences. However, renormalization can be used to eliminate divergences. Okay, that's extremely suggestive. So you actually, if you go all the way back to 1951, you'll find Schwinger saying you can ignore the actual definition of the normalization constants here. But you'll find Schwinger saying some very suggestive things about how we ought to think about renormalization. So he's talking about removing logarithmic divergences from amplitudes in QED. It says the logarithmically divergent factor that multiplies the Maxwell-Lagrange function may be absorbed by a change of scale for all fields and a corresponding scale change or renormalization of charge. Okay. It's an interesting way of describing a normalization. This is from a set of lectures he gives at Harvard in 1954. Again, he equates renormalization with a change of scale here. He says we can now change the scale of all quantities so that the theory contains only quantities which describe the long-time behavior of the particles. However, the form of the equations will remain the same as in the short-time theory. That is, we'll renormalize them. This is a clearly pretty physical description of what's going on when you carry out renormalization. He's not talking about divergences. He's just talking about sort of shifting our focus from short-time behavior to long-time behavior. Okay, and this is, again, we're as far back as the mid-50s now. All right, so there's a natural story you can tell. If you go look at a lot of Schwinger's work, he's clear that he thinks of renormalization as sort of separating out the high energy part where we don't really understand what's going on, and isolating the low energy part of the theory where we think that's fair, we think the theory is fairly reliable and we should trust it. That's a pretty natural way to interpret what he's saying when he says change of scale. That by itself would be kind of interesting, but not particularly compelling. He means something much more ontologically interesting than that when he's talking about a change of scale. And so that's what I'm going to start to turn to now. But in order to make clear what the ontological import of renormalization is for him, and like why he might actually think this, I'll say a little bit about the importance of measurement for Schwinger. Good. So the short version of this is that Schwinger thinks that the notion of measurement in any given theory is absolutely central to the foundation of that theory. So this is from a talk that he gives in some philosophical society setting in 1961. It's in the Schwinger archives at UCLA. Schweber reproduces a fair amount of it in the QED and the Men Who Made It book. So he says, we have to recognize a fundamental philosophical conception that physics is an experimental science and is concerned only with those statements which in some sense can be verified by an experiment. Blah, blah, blah. He says, in a sense, therefore, what is fundamental to any theory of a specific department of nature, which is a phrase I like a lot, is the theory of measurement within that domain. This is not idle talk for him. In a series of papers in the 1950s, he develops something that he calls a measurement algebra, and then sort of builds all of the mathematical scaffolding of non-relativistic quantum mechanics on top of that. So yeah, he starts from just like experimental facts about measuring atomic systems, and then attempts to use that as a foundation for building up quantum mechanics, sort of just from the measurement theory appropriate to the atomic domain. In particular, so he wants to tie each bit of mathematics in a physical theory to having some connection to a measurement process in order to assign it physical significance. So this is a quote from a Nobel lecture. He says things like this in a number of places. I chose the Nobel lecture because that's the, like, presumably he thought hardest about what he wanted to say there. But so he says, time appears in quantum mechanics as a continuous parameter which represents an abstraction of the dynamical role of the measurement apparatus. So time here is a parameter that's meant to capture the coupling of a measurement apparatus to some physical system. The picture here is from, he did a BBC, like a public science thing where he talked about special relativity in the late 80s. It's totally surreal. It looks like it was done by David Lynch. I encourage you to find this on YouTube. It's great. Okay, so good. The fact that time, the role of time here is just to represent the idea of some physical system coupling to a measurement device, means that time and the privileging of measurement for Schwinger means that time plays a fairly central role for him in how he thinks about organizing physical phenomena. So in particular, by the mid to late 1950s, he's thinking of physical phenomena certainly as hierarchically organized according to scales, but it's time scales that are the relevant scales for him. So there's ultimately a published paper by this title that is slightly different from the lectures that he gives here. I chose the lectures in part because they were given in Canada. Good. So yeah, these are given in 1957. The published paper comes out later in 1957 by the same title. I mentioned that at the beginning that one of his contributions in the 50s was the introduction of dynamical symmetry breaking. This paper is where he introduces this. Good. But I'm interested not in that so much as this hierarchical organization of particle phenomena according to timescales. So here he says, the electromagnetic interaction is a physical agency which destroys a kind of symmetry that would exist in its absence, in the sense that it distinguishes between charged and neutral particles. I mean, this is true. You start with some bigger multiplet, and then you start coupling the particles to different forces, and that starts breaking the multiplet up because you get mass differences. So he's returning to the idea of timescales. We might say that if an experiment extended over a time of 10 to the negative 22 seconds, he's previously introduced the timescales here as the characteristic timescales of the electromagnetic and the strong interaction. One would then begin to distinguish neutron from proton and the positively charged pion from the neutral pion by their associated mass differences. In the same way, much larger mass differences occurring in the heavy fermion group might be resolved by postulating some very strong interaction in whose absence hyperons would be absolutely indistinguishable from the proton. For such interaction, distinction of the particles becomes possible within 10 to the negative 24 seconds earlier than the electromagnetic case. So note here, he's talking about the timescales, he's conceiving them explicitly in terms of an experiment extending over that timescale. Basically an experiment extending long enough to capture the effects of the electromagnetic interaction on the mass splitting of the pions, for example. Okay. So this is why he's focused on timescales. The interactions occur over characteristic timescales, and those the interactions are going to contribute to the measured parameters of the particles. So what he takes us to suggest is that the introduction of the Baire parameters for individual fields, so when you write down a Lagrangian, you've got a Baire mass and a Baire coupling in that Lagrangian. He thinks that these are, in order for the fields to be physically meaningful at arbitrarily short distances, he thinks that the Baire parameters have to be what an arbitrarily quick measurement of the particle associated with that field would record. Arbitrarily quick because if you measure something instantaneously, it won't have any time to be, the coupling won't have any time to be renormalized by the interaction effects. And so if you let a particle couple to some measuring device on a longer time scale, then the measurement is going to incorporate the dynamical contributions to the parameters of that particle that come from any interactions between that particle's field and other fields where the interaction is shorter, less than or equal to the temporal interval over which the measurement extends. So you measure a Baire parameter that's meant to somehow capture, like the thing in itself before it's been tainted by interactions with other stuff. Thank you. Good. So what Schwinger takes from this is that the observed properties, the properties of particles that we observe in temporally extended measurements, the observed particles that those properties can't be associated entirely with any single quantum field. So this is again from that philosophical talk that he gives in 1961. He says, shortly after the introduction of the notion of a quantum field, says it soon became realized that the moment you have introduced the field in direct correspondence and in direct association with particles as we know them, so particles with properties that we measure over extended temporal intervals, inevitably this situation could not persist. We have to recognize that what we call physically an electron is only partially to be associated with that electron field. It is also partially to be associated with the photon field, because the two are in interaction. Physically, an electron can sometimes radiate a photon. It can then also reabsorb it. And these are a bunch of three-loop contributions to the electron's self-energy. This is just an electron propagating along and emitting and reabsorbing photons in a diagrammatic language you probably should not take as literally as I'm suggesting with my words. Okay. So this, good. I'll say a little bit more about the concept of a physical particle and how it relates to temporally extended measurement, because this is going to be important for understanding his sort of changing attitude toward quantum field theory through the late 50s and mid 60s. All right, so this is from a really, like a fairly incredible lecture transcript. He gave this is from 1963, I think. He gives it at Yeshiva University in New York. So he says, in a sense, the concept of a physical particle is one which involves sufficient time for its properties to be measurable with sufficient accuracy. So the very concept of an electron makes reference to the sense that we can measure it exists for long enough for us to measure its properties. For short time descriptions, obviously the notion of a physical particle becomes inapplicable. If one asserts that a more detailed description should be possible in seeking for something simpler, more fundamental than the particles as we observe them, it is not in terms of the physical particles that you must look for some simpler, more fundamental description. And he goes on after talking a whole bunch about energy momentum tensors to say that this more fundamental description is going to come from fundamental fields. These are the sort of substrate out of which the particles are going to, as we observe them, are going to emerge. So later in this talk, in response to a question, Fritz Rohrlich asked him a question about whether it wouldn't be better if we could do away with renormalization entirely. And this is where we get to the sense in which Schwinger's understanding of renormalization as a change of scale is particularly ontologically robust. He says, my objection to this is that what is customarily called the renormalization constant is a physical thing. He says, and that, for example, in the discussion I just gave, blah, blah, blah. He says, in other words, it is a question of whether beginning with a field with zero mass, there is or is not a particle with zero mass. That is not a mathematical, it is a physical problem. So for those of you who've done like perturbative calculations in a scalar field theory, scalar field theories, for example, if you write down a Lagrangian with a scalar field theory with no mass, perturbative corrections, renormalization will generate a mass. And so, and that's a sort of rough and ready sense in which you might think that a renormalization constant here, whether that's, whether a parameter is renormalized, for example, whether you can maintain a zero mass particle in your scalar field theory or not, that's a physical problem, at least as Schwinger's understanding it. And so he says, and so to me, the renormalization constants are simply an aspect of the fact you begin with a field theory, that the fields are the fundamental variables, the particles are the dynamical outcome, and in the process of reinterpreting the formalism in terms of particles, certain scale changes are necessary. So that's what he means by a scale change, is a shift from field to particle degrees of freedom. So the field, so to speak, is used as a particle excitation mechanism. Only part of the time is a particular particle excited. And so you change the scale. That is the process of renormalization. And then he goes on at the bottom here, he says, I would only mention the fact, however, that there are physical questions contained in the choice between whether a renormalization constant assumed to exist is different from 0 or equal to 0. That is a distinction between whether a particle of that mass does exist or does not exist. Good. So he thinks renormalization here, well, for a number of reasons, but what he's talking about here is that it's integral to the interpretation of a theory because it's how you move from the fundamental field theoretic degrees of freedom to the actual measured particulate degrees of freedom. Good. So that's the story. That's the sort of ontologically robust story about the physical meaning of normalization. This presents him with something of a problem. This, at least coupled with his insistence on measurement as a criterion of physical meaningfulness, presents him with something of a problem. So he says, the idea of a quantum field, this again is from his philosophical talk in '61. The idea of a quantum field as it arose historically was simply a convenient way of summarizing the mathematical properties of indistinguishable particles. He traces it, not here, but he traces this to like Dirac in the 1920s. Sort of the very earliest second quantization papers. But soon, through the ever-broadening developments of experimental science, what was here conceived of simply as a convenient mathematical idealization became reality. The ability as enough energy was available to produce the rest energy of particles, according to the Einstein relation, given the energy that corresponds to the mass a physical particle can be produced. And this is what's important. These alone then give the field its interpretation of symbolizing an act of creation, an element of physical reality. So we think of quantum fields, we sort of introduce them into our ontology by virtue of their role in creating and annihilating physical particles. This is the story he tells in this talk. It's a story he also actually tells in this Belfer lecture, although I don't have it up here. Okay, well, here's the problem, and this is a problem that he sets up for himself. I'm not reconstructing this. Quantum fields acquire their physical meaning through symbolizing the creation and annihilation of physical particles. He says, that, as we saw him earlier say, the particle concept, it's only meaningful at some, the notion of a particle is only meaningful at some temporal scale, tau here, if its properties can be experimentally distinguished by a measurement extending over some time interval from 0 to tau. Okay, quantum fields are defined at space-time points. Schwinger actually does know this is a problem. He doesn't seem to know about distributions, but he does recognize that this is an issue. And so Schwinger himself says that quantum fields are physically meaningful at points. They're meaningful at arbitrarily short distances, only if you can perform arbitrarily quick measurements of particle properties. And so remember, Schwinger thinks that an arbitrarily quick measurement of the mass or charge should yield the bare value of those parameters. Remember, they don't have enough time to be sullied by interactions with other fields. So if you do an arbitrarily quick measurement of an electron, you should just get the bare values. It hasn't had time to interact with the electromagnetic field. That's the picture. So this is the problem he sets up for himself. He thinks that quantum fields are physically meaningful at arbitrarily short distances or have fundamental physical meaning, only if an arbitrarily quick measurement can be shown to yield the bare mass and charge. That's the claim that he sets for himself. He then goes out to investigate this in the mid-50s, late 50s. One place in which he reports on this is in these lectures at Stanford that I mentioned in 1956. And again, he just reiterates the task he set for himself. The mass, the bare mass, mu0, appearing in the Lagrangian of some scalar field. and the absence of interactions implies it should be possible to exhibit the properties of a particle with that bare mass in the absence of any interactions. If a coupling term is present, so I mean, you don't get to measure stuff with no interactions. That's not how it works. You have to interact with the thing to measure it. So if a coupling term is present, as it must be in order to describe a physical field with sources, this then implies that in order to describe, well, that should be a particle with that bare mass, measurements must be carried out very rapidly so no interaction effects can interfere. And again, he translates this into a requirement that being able to measure the bare mass with an arbitrarily quick measurement, this translates into a requirement that you should recover the free propagator for the particle at arbitrarily high momenta. If you think of renormalization effects as incorporating the sort of dynamical effects of interactions between the field associated with a particle and other fields, over arbitrarily short timescales, there's no time for those particle parameters to be renormalized by interactions with other fields. Of course, this is wildly wrong. Like, it's not what happens. It amounts to a requirement that everything is asymptotically free. And so, but here's him saying this wildly wrong thing. So in other words, for very short time, and therefore very short space-time intervals, the propagator must approach the free propagator for a particle with a bare mass μ0. And the details here are not terribly important. He does a Lorentz expansion of this propagator, and then suggests that this is the term that measures the bare mass, because this is just the free propagator, and this is the first time that the mass of the particle actually contributes. That's the left-hand term, the farthest left term on the right-hand side is just the free propagator for a massless particle. So the mass first enters here to alter the propagator. So he says that this is the term where the bare mass contributes. This is the term that in some sense measures the presence of the bare mass. So he just imposes this as a demand. It's not a thing that he demonstrates. He just says that like this is required for the physical meaningfulness of quantum fields at arbitrarily short distances. You probably know how this is going to turn out for him. Yeah, it's not what happens. You get divergences from the, as we saw in Mike and James's talk, you get divergences from the high momentum end of the integrals. And so as Schwinger says a couple pages later in these lectures, the fact that the mean square fluctuation of the fields at a point is arbitrarily large evidently contradicts the idea of our expansion of a Green's function in a propagator in powers of gamma times the momentum. He's switched to talking about a fermionic propagator here, but the argument he gives in the fermionic and the scalar case is exactly the same. This is a scalar propagator he's talking about. The gamma p inverse is just the fermionic propagator there. So as if we try to limit the large momentum components, we can no longer make arbitrarily precise, and in parentheses, the bare mass measurements. We can't make arbitrarily quick measurements. And the basis of the entire theory is gone. This is just the expression of the fundamental inconsistency present in this field theory for small spacetime intervals. We expected in principle that quick measurements would yield the bare mass. He has this line where he says he claims to show that this is equivalent to the commutation relations, this measurability of the bare mass. I can talk about that in the Q&A. I will not say anything about that now. But this is not true. The effect of the coupling is arbitrarily large, which is what gives rise to the divergences. As you go to high energies, things don't get asymptotically free, at least in QED. Coupling gets increasingly large and you get divergences. Good. So what does he make of all this? This is in 1958, he puts together a selection of important papers in quantum electrodynamics, and he writes the introduction. And like shockingly appears a number of times in the book. It says, could it not be that the divergences are only spurious byproducts of an invalid expansion in powers of the coupling constant, and that renormalization, which can change no physical implication of the theory, simply rectifies this mathematical error? You might think that this claim here that renormalization can change no physical implication of the theory sits uncomfortably with what he was saying about particles and fields earlier. I'll say something about that in a minute. So he says, this hope disappears on recognizing that the observational basis of quantum electrodynamics is self-contradictory. He goes on. The fundamental dynamical variables of the electron-positron field, for example, have meaning only as symbols of the localized creation and annihilation of charged particles, to which are ascribed a definite mass without reference to the electromagnetic field. This is the bare mass associated with the electron. It's associated only with the electron field. So, and again, we've seen this claim already that fields get their physical meaning only through the creation and annihilation of measurable particles. Because accordingly, it should be possible in principle to confirm these properties by measurements, which, if they are to be uninfluenced by the coupling of the particles to the electromagnetic field, must be performed instantaneously. Same argument we just saw. He then points out that this is not what happens, like you can't do it. And so he says, thus, although the starting point of the theory is the independent assignments of properties to the two fields, they can never be disengaged to give those properties immediate observational significance. So he says, it seems we have reached the limits of the quantum theory of measurement, which asserts the possibility of instantaneous observations without reference to specific agencies. As far as I can tell, this just is a reference to the fact that we have a continuous time parameter, and insofar as time represents the coupling of a physical system to a measurement device, it asserts the possibility of instantaneous observations insofar as it doesn't pick out some privileged time scale. Time goes all the way down, so to speak. So note, what's interesting about this is that the claim here is not that this is a mathematical inconsistency, but that the observational basis of the theory is self-contradictory. It's phenomenologically incoherent, not mathematically incoherent, is the worry for him. Okay. So how does he respond to this? He doesn't respond. Remember, he's making this argument in 57, 58. He keeps working on quantum field theory until 1965. If you think the framework is, at minimum, observationally inconsistent, you might wonder what you were doing for the last 7 or 8 years. Here's what he does. This is where this distinction between, so there's a detour into the Schwinger model that I don't have time to talk about. This is actually, I think, is important for his thinking. Okay, good. I'm not going to say much about it, but again, ask questions and I will say more. All right, so this is where he introduces this distinction between fundamental and phenomenological fields. The inconsistency, the fact that you can't perform arbitrarily quick measurements of the fields, so they're not physically meaningful according to Schwinger at arbitrarily short distances. That doesn't mean that you throw the theory away. What he takes it to mean is that we're working with field variables that are not descriptively accurate to arbitrarily short distances, which is, in his lingo, we're not working with fundamental fields. The degrees of freedom are phenomenological fields. That's what we should view ourselves as working with, and he actually has a detailed story about how this works. Fields that are appropriate for describing particle phenomena on some characteristic temporal scale tau. They get their physical meaning by creating and annihilating particles whose properties can be measured, distinguished by measurements extending over some interval 0 to tau. So he gives, I'll come back to this. We'll give a couple examples. He's pretty explicit about it. But note, this is just, this kind of speaks to a fundamental loathing of speculation about arbitrarily short distances that Schwinger has. He doesn't say that, space-time breaks down or like field theory is inconsistent at arbitrarily short distances. He takes the attempt to extend the observational basis of the field theory to arbitrarily short distances. Just the fact that you can't do it means that we don't have any good idea what's going on. That's the story he wants to take from this. So as he says, it might be correct or it might be incorrect that we can sort of, even as an idealization, treat perfectly localized measurements as in principle possible. But it's a grave error to dismiss the concept on the basis of a priori notions of measurability. The idealized measurement concepts implicit in a theory must be accepted or rejected in accordance with the final success or failure of that theory to fulfill its avowed aims. Quantum field theory has failed no significant test, nor can any decisive confrontation be anticipated in the near future. we don't have reliable information about arbitrarily short distances. We're not going to get it. We're stuck working at a phenomenological level. So, good. The game, then, is to construct phenomenological fields that are appropriate for characterizing sort of dominant physical behavior at some given time scale. And to do that by making very weak assumptions about what's going on at, at shorter time scales. So, to give you an example, I'll start, good. Here's the picture of a phenomenological field, and then I'll give you an example of the kind of assumptions, like how weak the assumptions he's making are. So he says, throughout scientific history, one rarely makes direct contact between a fundamental theory and the observed phenomena. Instead, they're intermediate stages of phenomenology and simplified models. These are in some summer school lectures he gives at Brandeis in '64, but they're published in '65. To make progress with field theory at present requires setting up phenomenologically based models that reflect the general properties of the underlying fundamental theory. Only much later will one connect the fundamental theory with the phenomenological models. What has not been established in any general way is precisely how a phenomenological theory is derived on the basis of fundamental theory. This is not unfamiliar. We do not ordinarily go through a process that starts with protons, neutrons, and electrons and ends with a complete phenomenological theory of a helium gas, for example. Rather, we take the helium atoms as basic, and if we wish to use the field theory of many particle systems, we describe them by a phenomenological field. This, just to note in passing, Schwinger from like 1959 on makes analogies with condensed matter quite a bit. In the development of the Schwinger model, actually, he makes an example of, he uses an example of confinement in electron plasma, or some analog of confinement in electron plasma. Good. So that's the picture of a phenomenological field. You just take the field to create the physical particles appropriate for that time scale. That's the story. Just to give you a picture of the kind of weak assumptions that he's making about what the more fundamental dynamical degrees of freedom might be like. Here he's talking about sort of phenomenological baryonic and mesonic fields, B and M. You can figure out which one stands for which. Some of the qualitative dynamical concepts of a field theory of matter introduced, however, here's assumption one. By assuming the relationship between the fundamental fields and the phenomenological fields is predominantly local. That means the range of spatial dimensions involved in constructing the phenomenological fields from the underlying fundamental fermionic and bosonic degrees of freedom is small on the scale set by the inverse masses of the known particles. So if you sort of imagine the phenomenological fields as coarse-grained, B of X is a coarse graining over a very small, more fundamental spatial region. He says the picture is very crudely that of tightly bound constituents. And a second, not unrelated dynamical assumption is obtained as a qualitative inference from observed phenomena. It's that a satisfactory description of physical processes can be given in terms of the stable and unstable particles that are represented in the phenomenological fields. So that's the game. You make some very weak assumptions about how you would get the phenomenological fields out of the fundamental ones. And then you choose the fields that whose particulate degrees of freedom are enough to explain the phenomena that you're looking to explain at a given scale. Schwinger is actually quite interesting in this period in the sense that he's like explicitly in a number of places concerned with like explanation and explanatory questions. Good. So, however, I've been citing papers from '64 and '65 where he's talking about this fundamental phenomenological distinction. Not long after making this distinction, he abandons field theory entirely and starts working on source theory. Source theory is basically like if he focused on the phenomenological fields and then turn the dial all the way to the right, you end up with a very phenomenological theory, and that was what he was hoping to develop in source theory. In particular, he wanted to get rid of operator-valued quantum fields entirely. So he continues to work with phenomenological Lagrangians through the late 60s, but the post-1966 work basically exerts monotonically decreasing influence on the mainstream of physics. However, aspects of so in particular, the work with phenomenological Lagrangians in the late 60s that's happening like as he's trying to build source theory and leaving quantum field theory. These are picked up by others working on low energy, strong interaction physics at the time. So in particular, who were working on soft pion scattering. And the most notable person that's influenced was Steven Weinberg. And I'm going to say a teeny bit about, remember the big picture here was how Schwinger's work is related to the development of effective field theory. I'm going to gesture, hopefully very suggestively, at a link and then stop talking. All right. So this is one of Weinberg's earliest papers on phenomenological Lagrangians or effective Lagrangians for soft pion scattering. You want to bounce pions off each other very gently. So the paper itself is important and influential in like both the field and Weinberg's later development. But note, he says here on toward the end of the paper, it's remarkable that the Lagrangian he's written down, which is his effective Lagrangian for soft pion scattering, is to be used only in lowest order, with the effects of loops, et cetera, already being accounted for by the presence in 9 of, these coupling factors are just, they function as renormalizations. They're input parameters that are taken from experimental data. So just how does this come about? If we knew, we might understand more deeply the dynamical basis of current algebra. Note, so in this respect, our method is reminiscent. He cites, there's a note 11 there. In this respect, our method is reminiscent of the recently developed source approach of Julian Schwinger. I wish to thank Professor Schwinger for an interesting discussion on this point. So there's actually there are 4 or 5 papers between Weinberg and Schwinger that where they acknowledge mutual influence in their work on effective Lagrangians in the late 60s on mostly on soft pion scattering. And so, yeah. The motivation and some of the methods he uses actually end up exerting a fair amount of influence on Weinberg, who then, of course, comes to be a central figure in the development of effective field theory in the mid-70s. And I'll end with this. So this is the paper, for those of you who have heard the slogan that quantum, if you want a theory that satisfies quantum mechanics, Lorentz invariance, and an S matrix that satisfies cluster decomposition, you get a quantum field theory. Like you just write down the most general theory that satisfies those conditions, you get quantum field theory. Weinberg, that's how Weinberg teaches field theory in his textbook. This is the paper where he actually presents that argument in 1979. It was presented to Schwinger on his birthday. So Schwinger's ideas have strongly influenced my understanding of phenomenological Lagrangians since 1966 when I made a visit to Harvard. Blah, blah, blah. He says, in the decade since 67, Schwinger's ideas have evolved into what he calls source theory. I've been pretty much out of touch with this work, mostly because of an involvement with other lines of research. That's very kind. Everybody's out of touch with this research, with Schwinger's work. Nobody cared. But it's his birthday. But perhaps also because I found Schwinger's conceptual framework unfamiliar. Recently, several problems have led me to think again about the use of phenomenological Lagrangians, and I find that my ideas have shifted somewhat to a point of view that seems to me to be now not too different from the point of view of source theory. Remember, this is the paper where he sort of makes a very foundational contribution to the development of effective field theory. Although I have not tried here to judge the extent to which the ideas described below overlap those of source theory, I would not be surprised to find that these are points which long ago appeared in Schwinger's work. In that case, I hope you will take this paper as a little work of translation into the Vulgate, offered as a birthday present to an old friend. This is nice. It's his birthday. You might think he's being charitable. Weinberg has basically maintained this line about Schwinger's influence for the subsequent 40 years. So, yeah, this is sort of a tantalizing connection toward the early days of effective field theory. Yeah, between Schwinger's work and the early development of effective field theory. That's sort of the future of this project. Done. Thank you.
Okay, questions. Put your hands up. I'll add you to the queue. Okay, James?
Yeah, I was wondering about Schwinger's argument for thinking that the charge diverges in QED or something. You said that he demanded that as you go to arbitrary high energy, that he basically manifested about freedom, but then he had some argument for
why you don't.
Yeah, is the argument just ultraviolet divergences therefore?
Basically.
Okay. Pretty unsophisticated.
No, that's right. There's like this very complicated roundabout argument to get here. But of course, like what you see is not that you get the free propagator at arbitrarily short distances.
Yeah, that's true. I mean, yeah, okay.
No, that's basically it. All of the sophistication goes into this claim that.
So he wasn't interacting with literature about like Landau pole and like
no, good.
Stuff.
Good. So this is yeah. I'm glad you asked. He's not, and in fact, the most. Well, I won't go all the way back. The question I began with is like, why didn't Schwinger develop effective field theory? Part of it is that he, I mean, to be fair to Schwinger, like many other people, doesn't seem to have, if he read the Gelman-Lowe paper, he forgot about it because in some notes, like some personal notes in the 70s, he writes about like revisiting the I went and read the Gelman-Lowe paper after he reads something that Wilson wrote. And then, but like at that point, he then says like, yeah, this renormalization group stuff still seems silly to me.
Yeah, I think there's a interview with Gelman where he's describing Schwinger giving a talk about the ultraviolet behavior of QED. So probably this stuff. And apparently he complains a lot.
It could be. It could also be later in the 70s. So Schwinger returns to this in the source theory framework and tries to redo a bunch of the QED at short distances work that Gelman and Lowe did in a source theory framework. So it could be that. I don't know. It's not clear he ever gave talks about this. He gave it in summer school lectures, but I don't know like whether he was going around to give colloquia about this.
Yeah.
It's also worth noting that.
I remember where I read that about Gelman.
It's this interview and those like there's the YouTube things. Yeah. It's also maybe worth noting in this context that Gelman and Schwinger, like personally, there was considerable acrimony.
Yeah.
And so it's not clear. For one, that probably played some role in Schwinger not reading the Gelman-Lowe paper because Schwinger was like a voracious consumer of the literature. But it may also have influenced Gelman's recollections.
Yeah.
Josh?
Yeah, so I'm wondering if you know anything about how Schwinger felt about virtual particles. You showed the diagram for like the self-energy of the electrons, and then like this distinction between the fundamental fields and the phenomenological fields, and like the measurement criteria for meaning.
Yeah.
Does he ever connect that to the virtual particles and like take a stance on it?
Not that I'm aware of. I mean, he thinks that like vacuum polarization is a real physical phenomenon. But he doesn't say stuff about like, he doesn't couch things in virtual particle language. So I put diagrams up on the board. That is not Schwinger's doing. That's from some effective field theory paper from 2007 or something. It just had nice diagrams. In fact, Schwinger avoided finding diagram methods. He would kind of sigh when his students used them. In part because he didn't, that's less about a personal issue and more about Schwinger's concern, which he's quite explicit about in a number of places, that people in the particle theory community at that point are equating quantum field theory with perturbative quantum field theory. And insofar as the diagrams are perturbative tools, he would like to be freed from them. So the short answer is no, but there's reason to think that those are just not exactly the terms in which he thought.
Eduardo?
Two comments. I had one, then after this question I have another. I personally, along the lines of what you said, which I would totally feel like aligns well with what I think as well. Virtual particles, I don't think should be given any seriousness at all as a limit of physical reality whatsoever, because virtual particles only exist within perturbation theory. It's a way of mathematically think. Our brains like to understand processes that kind of make sense, and we do a perturbative expansion, and we use those notions to try to do it. If someone explains some phenomenon through the virtual particles, someone else can say, oh, but I solved the problem non-perturbatively, much better than you. Where are the virtual particles? Nowhere to be found. So honestly, I don't think anyone should Then again, as you said, like, of course, vacuum polarization, that's not about virtual particles, that's a real thing. And the other one, the real question that I have is, so source theory, I mean, I don't know much about source theory at all, but isn't so what I know about Schwinger, and correct me if I'm wrong, because I know very little about this, it's more like that Schwinger had, and maybe that's what source theory is, I'm not sure. It's not really a theory in its own right, because what like quantum field theory would be, because theories to me in physics are frameworks. What I understand, and correct me again if I'm wrong, is that source theory is more a way of understanding QFT still. So it's no different from the framework of QFT. Rather, it's a way of understanding QFT in the presence of sources, right? Isn't that right? Or
so,
if I'm wrong, say it.
Yeah, I mean, because like there's a sense in which, how should I put this? I mean, the short answer is I think that's not quite right, but so in particular, I mean, the framework is different in the following sense. You're not working with operator valued fields for one. Like you do not see operators, full stop, or you don't see field operators, full stop. What you do, so like it uses a lot of QFT machinery.
That's maybe why I'm confused.
Yeah, but I mean, it's how should I put this? In some sense, it's not that different. The reason he's doing away with operator valued fields is because he wants to do away with what he views as like undue speculation about the structure of the phenomena at arbitrarily short distances. And he thinks that operator valued fields are like, to the extent that they're not tied to being defined at arbitrarily short distances, they're just like such a mathematical mess that there has to be some other framework that he can work in. That's the story he wants to tell. When he does source theory, I mean, basically what he's starting with is, he starts with like creation and annihilation, just the vacuum expectation values, or the vacuum amplitudes, transition amplitudes. And so he's like, in some sense, borrowing stuff you know about field theory, but trying to do it without introducing field operators and renormalization and all that. That's another thing, is he wants to get rid of renormalization because, as he says, he thinks that that's to move from the fundamental field degrees of freedom up to the particular degrees of freedom. Source theory, like the starting point is the vacuum amplitude for the creation of a single particle. And then it propagates, and then you have sinks. And so it disappears back into the vacuum. That's his starting point.
Let me put it in the form. If I were to perform a calculation in source theory, how different would it be from performing a calculation on effective field theory?
It's harder. But it's like, it looks sort of familiar. Did you?
It's harder, and it's, Schwinger famously was said to be the one who would, I guess the quote goes,
other people calculate to show you how to do it. Schwinger calculates to show you only he can do it.
And it really only he could evaluate the source theory expressions. But at the end of the day, I don't know if this answers your question, but a lot of the targets, a lot of the he's very committed to getting the numbers out at the end of the day. I mean, this is like a methodological stricture that runs throughout his entire intellectual life. And so the elements of our empirical basis for commitment to the empirical adequacy of quantum field theory is something that it's deeply entrenched in his thinking. And so a lot of the source theory work is dedicated to showing that in principle, he can, like, whatever you can get from your quantum field theory description, which has this kind of ontological overreach in his view, he can do it, and he can do it at this purely phenomenological level, and he thinks that that's a much more epistemically safe way to proceed. But
so like philosophically, in some sense, it's quite similar to the effective field theory strategy, but like the actual calculate, like you're not going to see, like at no point will you see loops, at no point you'll see anything like
You
this.
see, with this explanation, I would say that to me that would be an effective field theory too. That's what it does, right? Field theory.
So that's good. If you expand, like if you have a very broad notion of effective field theory, then like that's, like he's not like, he doesn't have like, he's not expanding around a fixed point and then suppressing irrelevant operators and stuff like that. None of that shows up. But the broad sense of like restricting yourself to a limited range of scales and using the degrees of freedom appropriate for characterizing phenomena in that range of scales, that's absolutely what he's doing. That's the motivation.
So, for example, the calculation that comes to mind, the lamp shift.
Yep.
The lamp shift is certainly a very quantum field theoretical phenomenon. However, the way it's computed is not.
Yeah.
They do an effective theory that is not in the sense that it's not a QFT in the sense that you're saying, oh, let's do away with the distribution operator distribution. Oh.
I know what you mean, yeah.
Let's do away with the objects, the quantum fields as operators, and let's compute in an effective way, and you get the right results that you can get in an experiment. So that's to me, that's an effective field theory as well, even though it's not there. And in that sense, would it be similar then? Or not really at all?
I think, yeah, I mean, I think that similar, I think. But maybe, I think the similarity is more in spirit than at the actual...
Sorry, in spirit.
Yes, absolutely, then yes. But it's not like the actual machinery of how you get to the source is quite different.
In that sense, and maybe that's my use of things, when I talk in physics about theories, it's a different framework to do things.
Good.
And I distinguish that from an effective theory, which is coming from still the, I don't know, in the hierarchy of structures, right? I feel that this is still QFT.
Good. Yeah, so good. Schwinger both, I guess I should say, Schwinger, he wanted to emphasize that source theory is somehow quite different. It's not clear that it was as different as he wanted to say it was sometimes, and many people didn't buy it. So he wrote books about this. He wrote a couple textbooks on source theory. Whiteman actually reviews the first one in 70 or 71 or something. And Whiteman says, like, basically this is disguised quantum field theory, but like made way harder. Yeah, and yeah, that's basically, so that's many people saw it that way.
So doing away with operator value distributions, to me, wouldn't be enough to call it a theory, I guess.
Yeah.
I guess. I mean, anyway, I'm not a philosopher.
No. It was, that's right. I mean, I don't have any particular, like any real prescriptive notion of what a theory is. Like, I think there's a broad sense in which you could just call this like an effective theory. And yeah, I don't remember. Do you remember if he ultimately thought that this was like a temporary retreat that would then make contact with, so he doesn't by the end of his career, but initially I think there was some thought that like this was a more perspicuous framework for organizing like low energy strong interaction phenomena. This was kind of a temporary retreat, and then maybe once like we figured out like a good organizational schema, you could then, like, that was a good basis on which to then launch further speculation. But it's unclear whether he wanted to reintroduce, I think he did not want to reintroduce operator value fields, but instead wanted to extend the source theory technology sort of scale by scale down to higher energies.
Right. Thank you. That was good.
There's a question over here.
Yeah.
Did not Schwinger's 1951 paper that you were referring to, did it not influence the development of Feynman diagrams and so many other calculations that come in, including photon scattering?
So the paper is extremely influential. The gauge invariance was on gauge invariance and vacuum polarization paper in 51. Yeah. That's it's extremely influential.
Because Feynman diagrams, in fact, seem to have developed a lot, starting from that Lagrangian formulation.
No, that's absolutely right. Of course, Feynman has the diagrammatic methods before the paper. Schwinger certainly, but Feynman diagram technology didn't. Just like fall fully formed from Feynman in 49 or whatever. That's the answer, yeah.
Would Phenomenological have any sort of developments similar to Schwinger, or do you think they are very remote from each other?
Would Feynman have similar developments to Schwinger? Is that
Phenomenological. I'm speaking about Phenomenological.
Oh. Sorry, I misheard you. So it's interesting. Tominaga and Schwinger have like oddly parallel career paths. They both did. They both worked on radar during the war, and they both described their experiences doing radar calculations quite similarly. Where, like, as a as a theorist, you're like, oh, I have to do stuff with electromagnetism. I'll start with Maxwell equations, and then very quickly you realize that's dumb and complicated. And you bundle a bunch of stuff into phenomenological parameters, and you do like these kind of effective circuit calculations, which is actually, that's what Mike's looking at now. But aside from, and then they develop like a very similar dynamical basis. There's a reason that the formalism that Wayne talked about yesterday morning is called the Schwinger-Tominaga picture. They both kind of hit on this more or less independently. Other than that, I mean, a lot of the Tominaga stuff is in Japanese. Tominaga then, which I do not read, I guess I felt like I didn't need to say that. I can't read a lot of the Tominaga stuff, and there's actually not that much of it, in part because he kind of ascends fairly quickly into like a position of university bureaucracy, and then I think has some kind of like quasi-political status in Japan for the remainder of his career. I also think he was a bit older than Schwinger, is that right?
Not sure.
Yeah, so I think that his, like the productive phase of his career kind of topped out more quickly after the renormalization work than Schwinger's would have.
Chris?
Yeah, I was just curious about the idea of measurement being central, but the fact that he's focused on measuring the bare parameters of Lagrangian in particular, that seems odd. Were there other people who were also, I mean, because just in contrast to say Eduardo's this morning about measuring local observables, that's a totally different, it's still kind of an operational empiricist approach, but why was he focusing on bare parameters in particular?
It's a good question. So yeah, I guess I have this, where's the, yeah, good. Here's, so I think there are two things to say. One is that he thinks that insofar as, I mean, he clearly does think that like, if you want to associate a particle with each field, like individually, like the electron field creates electrons, and you don't have to talk at all about the electromagnetic field. Then what it's going to do is create, like that's the bare mass of the particle that it's going to create. It's going to create an electron with the U0. He thinks, I mean, and like really, he's quite serious about the fact that insofar as some parameters, some mathematical structures in your theory, it should have some connection to measurement. So that's one line, is just this like hard line tying of physical significance to measurability, in the sense that like if a particle, insofar as the particle notion both is meaningful at short distances and can just be like associated directly with a field, what you're going to get is the unrenormalized bare mass if you do an arbitrarily quick measurement. So that's part of it. He has this argument as well. So we expected in principle that quick measurements would yield the bare mass, and showed this assertion is equivalent to the commutation relations, which hold for all times. Yeah, we can do that. So what he does is he's working with time-ordered Green's functions, and he wants to look at, he wants to look at arbitrarily short time intervals, which means that if you have like a different, you've got different Green's functions and you're going to sort of bring them together. What needs to happen is he wants to take an average of like the advanced and retarded Green's functions to stick them together. That involves, in order to take, the way he takes that average involves basically having the fields commute. And so the fact that the commutation relations hold is what allows him to sort of consider a Green's function basically at the same time, at arbitrarily short times. And so that's where that claim is that you need to invoke the commutation relations in order, like if you want to impose this requirement, you can then invoke the commutation relations to ensure that it's satisfied. He doesn't show that it goes the other direction anywhere I can find. So he doesn't show that it's equivalent to the commutation relations. At most, he shows that the commutation relations, it's necessary for those to hold in order for him to make this argument about the Green's function behavior. But if, like if he really believes that, then presumably that's also why he's focused on the bare mass. Like if you think that the commutation relations entail that you should be able to measure the bare mass, then it's just like built into the foundations of the theory for him. Yeah.
Any other questions? If not, let's thank Porter.